Good afternoon. Welcome to the stream. I don't know about you, but I'm pretty excited to start a new chapter. We did our little side quest of building a web-based compiler explorer in Gleam, which was fun. And we'll revisit that again in the future. There are a couple things that I want to do on it that I've kind of queued up. I might do them off stream, but since, I don't know, people seem to like that content, I may come back to it and we'll do some more with it and make it look even nicer. In the meantime, we're going to start a new chapter. This chapter is chapter 6. We alluded to it when we were finishing up chapter 5, of course. And that was, we're going to talk about tuples, or tuples, depending on who you talk to, and garbage collection. So when we say tuples, we mean product types. Heterogeneous collections of fixed size. And this is basically, in any other language, you'd call this a struct, right? At the base of it, you can think of tuples as structs with unnamed fields. The fields are just referenced by their index. So we'll be adding those to the language, and maybe we'll dip our toe into what the garbage collector has for us. But we're going to see how far we can get today. I think it's pretty neat because it introduces a whole lot of interesting things. You know, so far all of our types have been well known, known statically at compile time, and also are either they can fit into a register or they can fit on the stack in one slot on the stack. But with tuples, we no longer necessarily have something that can fit on the stack, and it definitely can't fit in a register because you can have as many things in there as you want, roughly speaking. We'll have some artificial limits on it for various reasons, but you now it's say, well, where do you put that? You can't. You could choose to put it on the stack, but that's not typically what happens. And the other thing that's interesting about it is that tuples can contain other tuples. So their type will be known at compile time, but we're not defining those types. We're inferring those types based on the usage. So there's a whole lot of problems that would potentially be alleviated if we had the ability to declare these product types, in that we could decide ahead of time where to allocate them. But then, maybe we wouldn't learn what we want to learn. So today we're going to learn how we can put these things on the heap, how we can reference things inside them, and deal with their lifetimes, and that involves garbage collection in this model. So that is an explicit decision on the choice of the authors of the book that we're working through, Essentials of Compilation, and I think it's a good thing to learn. So we're going to get into it. Before we actually start the tuples and garbage collection bits, we have a little bit of things to fix. So if you want to follow along, of course, always follow the repository here on GitHub, Sean Cribbs, Essentials of Compilation. And I noticed we had a failure in our GitHub workflows. So looking at this failure, you can see that actually it has issues with, well, it has a couple issues. There's some warnings that we saw last time related to parsing, but we have, you can't find this. And I don't think that it's as important to be able to, right now, run the CI suite on the JavaScript platform. Now, the solution to this would be we run npm install before we run Gleam test. But since we are not doing that here, it's probably better that we just switch this target away from JavaScript and back to Erlang. And then we might create some additional CI steps at a later date when we want to go back to working on the UI. So if I run Gleam test here, I'm going to get no failures. And of course, when I was running on local machine, I wouldn't get any failures either, because I'd already installed the packages that we depend on with npm install. So we don't have that issue when we're running on the Erlang target. So I'm going to switch that back, and we're going to say switch back to Erlang target for tests, and we'll push that. I'm not going to check in on the actions. I'm pretty certain that they will work. Note that if we go in here, we would need to, we probably should add some more steps in here, but this will be sufficient for now. And I think that we have a problem here too, that we need to switch the Gleam version. Let's see. That doesn't tell me what I want here. We're on 28. So let's switch the OTP version to 28 unpinned and the Gleam version to 1.12.0 while we're at it. Did I not commit? I apparently did not commit. Okay. And we're going to just force push. Okay. That'll keep us up to date with the version that we care about for Gleam. All right, so let's have a look at the book now. So this is, here, hide the sidebar. We're going to talk about the heap, about garbage collection, and they say multiple times in this chapter, from the programmer's viewpoint, that a tuple lives forever. That's not strictly true. It is used, or it lives until it can no longer be reached by the garbage collector. So we're going to extend the L-while language, and some of the improvements we did in the last chapter in terms of the different phases and what we're doing there will help us move forward. We can just rename some import aliases, and that'll make things easier for walking down the stack, as we tend to do when we build this stuff. So we're going to add the L-tup language, and again, so it extends the L-while language with tuples, and the operations that it adds are vector for creating one, vector ref for reading an element, and vector set for writing an element. And there's also vector length for containing the number of elements of a tuple. Here's an example program. We'll probably use this one to kind of poke at our the top levels of our compiler. Key to point out here, if you've not done this before, so Gleam, it has tuples. We can do like A, B, C, and that will create a tuple of type 3 elements, where the first element is the type of A, the second element is the type of B, and the third element is the type of C. We're doing a similar thing in here, in that we don't declare them. So in this example, they're creating a vector where the first element is an integer, the second element is a Boolean, and the third element is another vector which has its own type of one element which contains an integer. So they are 0 indexed, it looks like. So if they say, vector ref of t, so t was bound to this vector ref of t slot 1, which would be the Boolean. So what we can do in our front end is we can look at all the vector types that are created, and we will know the type of this variable. And when we get to this spot, we can check, is what is the type of this expression? Well, it's a Boolean taken from inside this vector. So we have some steps to do there to make sure to propagate that information through our type checking. And then of course it's referring to slot 0, which is 40, and adding that to so they were doing a double deref here. So it's like get the vector, or get the slot at 2, which is this vector, and then get slot 0 out of that vector. And yeah, so if it is true, then we return 42, otherwise we return 44. Okay, so this sort of paradigm, they say, raises several interesting issues. First, a variable binding performs a shallow copy in dealing with tuples. So that means that different variables can refer to the same tuple. So we basically have pointers. We don't really have pointers. It's just that another way to think of it is we have aliasing. Whereas before, when we had discrete values, just integers and booleans and void, those can all be, they can all fit in a register, and they are trivially copied, right? Whereas the size of these vectors, hi Chris, thanks for coming to the stream. The size of these vectors, it's technically, like I said before, it's technically known at compile time, but it definitely does not fit in a register. So we have to put them on the heap, which means essentially if we are creating a new variable that refers to a vector, and there's another variable that refers to that same vector, they're essentially pointers. On the stack or in a register, they're pointers. So we need to be able to allocate onto the heap and put these structures onto the heap. And we'll get later in this chapter into the representation of those, which is really interesting. But for now, you can think of, well, you could bind, with this let expression, you can bind t to this vector, and then you could immediately go let, u bind to t, and now u and t are interchangeable, and they actually refer to the same thing rather than just copies of the thing. So that's what they mean when they say a shallow copy. It's just copying the pointer to the thing. Okay, so we have aliasing, which is interesting. In this following example, T1 and T2 refer to the same tuple value, and T3 returns to a different tuple value with equal elements. Okay, so T1 in this example refers to vector 3, 7. T2 refers to T1. So this is basically like copy the pointer. And T3 is an equivalent vector, but it's allocated separately. So T3 is not an alias of T1 or T2. So if T1 and T2 are equal and T1 and T3 are not equal, then return 42 or 0. So there's an interesting question in here about how we implement this equal. Is that these things are the same object? I say object in the general sense, not in the like OOP sense. Are these the same object in that they are refer to the same place in memory, or do they have contents which are equivalent? So we're introducing all sorts of semantics changes here that are going to be interesting. So the other aspect of aliasing is that you can mutate the contents of that vector through either alias. And like now as I'm thinking of this, like now you know why Rust made all those decisions about, well, you can have as many immutable aliases as you want, but only one, one exclusive mutable alias. You can see the problems that can occur here. It's not even to do with concurrency. This is just, what is identity, right? Okay, so in this example, they're setting t1 to the vector of 3, 7. They're creating an alias of t1 to t2, and then this let vector set thing is kind of bonkers. They could have just done begin, but my variable thinks therefore it is. Yeah. So here they're setting slot 0 to 42 on t2. But since t2 is an alias of t1, that basically sets this to 42. And then you refer, or you get the field out of t1 in slot 0, you're going to get 42. So this is like mutations visible through aliases. Okay, and then they're talking about lifetimes. When does the tuple's lifetime end? Essentially, it's forever, but essentially until it's unreachable. We don't include any operation for deleting tuples, right? There's no notion of static scoping for them. You can't just, in the Rust parlance, you can't just drop them when they fall out of scope, because they can be aliased. You can return those aliases. You can return fields from inside those tuples. You can, so they're like, you've opened up a whole slew of problems with understanding when to get rid of something. And garbage collection is a general solution for this problem, but it doesn't constrain memory in the way that Rust's like RAII drop thing would constrain the use of memory. Anyway, and explicit borrows is the other thing that Rust adds that makes that simpler to understand. Okay, so let's go back up, and we're going to add the syntax. So here's the concrete and the abstract syntax. So we're gonna do our little dance here that we've done before. We're gonna copy. Yeah, we're gonna duplicate L while, and we're gonna call it L tup or L tup. Yeah. Okay. So we have. We're going to have a vector type that we need to add, which is going to contain a list of type. So we have to have types for each of the contents. And now that we've made this type, this Gleam type recursive, self-recursive, we can contain vectors that contain vectors in the type representation. Okay. So now let's go down to expressions. This is not a primitive. Let's look at the abstract syntax. Oh no, they do create primitive. Okay, so this is the concrete. This is what we'll put into our parser. These things, and that'll be interesting too, because we have any number of sub-expressions, whereas in our previous things we always had fixed numbers, like I know that a lot of Lisps allow you to say do plus or times with any number of arguments. This language does not. It allows only 2 arguments for that operation. You could add that on top and just compile it out to multiple. But here, this is any number. Note there's a star on here, so that means you could create. It's going to be useless, but you could create a vector that has no contents. So let's look at. It's interesting they say this is op in the abstract syntax. The op is vector or vector length, and that's because it's primitive. I think that actually because we did that differently, we say this is actually prim op, not not the comparison operator. Okay, so we can say vector, and this is fields. That's going to be a list of expressions, right? Oops, no commas. I'm doing other languages. Vector length. And that's going to take 1 argument, which is just an expression. And then it's interesting that they say that's an op, but these have specific ones. I'm kind of confused there. It's still a primitive. The question, yeah, this is concrete. We're concerned with the abstract syntax here, and we'll look at the concrete syntax. We'll pop up a level and go to the parser here in a second. So okay, so there's no, we ran into this with if and some other things, in that this has to be an integer, but it's a question of when do you enforce that. And I think that what we can do is, when we're type checking, we can say, what is this thing? If it's not an integer in that spot, then we'll create a type error. Otherwise, it's just an expression. So it's like this is 2 expressions and this is 3 expressions. I think that's probably the way to go. And again, this is not. Excuse me. This is not an expression in the same sense. This is a primitive operator. Okay, so we need vector ref, and that takes the vector, which is an expression, and the index, which is an expression. And then we need a vector set, which is, that takes the vector, the index, and the value. And then that's all the new concrete syntax. Okay, so what do we have wrong here? Aha. So we're going to have to deal with interpretation, which will be interesting. Let's go back. We're going to have types which are right. So I values, we are also going to have a vector value, which is going to be a list of I values, right? So that's to start. Now we're going to have issues with this. We have to add, I don't know if they have a definitional interpreter in this chapter. Here's their interpreter. So okay, so here they're looking at we'll have to get to that because there's a has type thing that they haven't talked about yet. Let's look at the type check. Okay, and then we need to add another one here and say this is vector t type error. Okay, so this is, we've got a vector type, we're supposed to return integers. I don't know if that will remain the same as we evolve this language through the book, but for now we are only allowing integers to be returned from our programs, which makes sense for, you return like an integer on a POSIX operating system, you return an integer as the result of the program. That's not really what this is for, but for now we only allow integers to be returned. Okay, so now we should be missing expressions. Yeah, so let's go down here and why can you not just add the operator? All right, we're going to scroll. Okay, so we have this operator is allocate a vector. What we need to do is so this is like this result okay, so we're kind of threading through the operator and the type. And why are we doing that? Okay, so we should get a program. Okay, so the type env here is a, okay, binding variables to types. Okay, so here it's like we're inserting when we get okay, I'm going to make to do there, and we'll have vector length to do, and we're going to have vector ref. to do, and we'll have vector set. So I think the only one that could potentially, well, unless they have nested expressions, which don't type check, the only one that could potentially fail is the vector set. If we know the type of v, and we're passing a value which is of a different type than the field at that index, right? So what we're going to do, let's go ahead and this is sort of like a fold. Let's see if we did a fold in any of these other things. Yeah, we did fold until. Okay, so we'll do something similar to this with our expressions in the inside the vector. Okay, that should be straightforward. So we're going to say let expr types exprs we'll do list fold until, and there's okay empty list, and then we'll have a function which is takes okay, continue or stop. And what did we do above? Oh, we have to list reverse so that we're building the list in the correct order. Okay, so we'll just do this. Except it's not statements, it's expression. And here, let's again crib from this. We're going to type check expression. Except here we do care about, so we're not going to throw this away. We actually want the expressions and the type. So I think kind of what we want is, rather than this list, we want a tuple with two lists. Inside this result. And we're just going to rebind exprs. So let's do a tuple. So one has the expression and one has the type. And then we're going to say okay, so this is just pulling out the inner part of OK, this result map, right? So we know that this is a tuple, and we're going to say, can I pattern match on that? Let's say expers types, and we will say I'm going to call this E1. We're going to say E1 expers, right? We're going to cons it on there, and we'll say T1 types. And I think that it doesn't like this. Right, lists of A, list of B. But we're not pattern matching on it. So let's do so we're going to say I got the Gleam syntax wrong there. Okay. So okay, so we need, let's keep that to do in there. So at least we can check this. It's just saying it's not used. So like we did up in begin, we can do a use there. And we'll say let's rename this to checked. Honestly, we could dump this entire thing into this result try, but yeah. Okay, so now it's correctly finding that this is a list of expressions, a list of types, and what we need to return from there's nothing else to check here, right? Like as long as the nested expressions are like type check, then really what we want to do is probably not result try, but result map. And then we can say we're going to return vector of expers and vector t, right, of types. Does that make sense? Okay, so let's think about vector length. Vector length, we need to make sure that the, okay, it is v. Okay, so we need to make sure that the type of v, okay, so this is going to be an expression and a type, and we want to do, so let's say this is expression and type. We want to make sure that actually, this is probably no. We want to actually have to return. So if it's a vector, then what we want to return is the expression and type. If it's anything else, then we want to return error and a type error. And this is where it's going to get a little tricky, in that, well, I guess we could return a vector t of empty list. Yeah. Okay, so type error is actual expected expression. Okay, so actual is other. Expected is vector t. And we'll say empty list. And the expression is vector length v. Except it's prim. Right? What's wrong here? I need another parenthesis. Oh, okay. So we need to reconstruct, because this was the inner expression, right? The v. Okay, so this is vector t, right? So if we didn't get a vector t, then we should return an error there. Okay, and so we'll do a similar thing here for vector ref. This is vector ref. Let's call this v1 vt, and we're going to say we did this type check, or check type equal. We could say we need to also do the index here. The question is, should it come first or not? You know, and then we'll do we still need to do result try, right? So we'll do use result try check type equal, and we're expecting integer t, and we got it, and the expression, what are we using the expression? Okay, so I1. Okay, so we'll say vector ref I1, and then the type here that we will be returning is a bit more interesting here. So we need here. I think we need to do this. So we need the other thing here is that we could potentially return a type error when the index is out of bounds. But given that this we are checking an expression, and maybe what we need to do here is make sure that, like, if you look over here, right, note that this says this needs to be a static integer, not an expression. So I think that what we need to do here is not check that it's that. What we need to do is make sure that it's the literal that this expression is a literal of integer, right? So how can we do that? We could say I'm going to do it with nested cases for now. And we're going to have to make a new type error, which is we're going to need two of them. We're going to need one, which is index out of bounds. We'll say vector index out of bounds. And this is, we'll have actual, which is an int, and we'll have limit, which is an int, which is the size. We'll just say size. And then we're going to need to vector index is not integer. Very verbose. And then we'll have an expression, which is the expression that was put into that position. So like we're kind of dealing with the problem of what is the concrete syntax versus what is the abstract syntax. And in the abstract syntax, we don't allow non-integer indexes into vectors. Like, not in the sense of types, but in the sense of, like, this needs to be a literal. So maybe we could say yeah, we'll leave it at that. So where were we? Way down here. Okay. So if and we can reuse this this bit of stuff. Maybe we can extract it into a function like we did with check type equal. That would be nice because then we can do result try in here. So let's do, say, check vector index, and this is an expression. This result of an integer or a type error. The other thing that we could do here is since we're already checking the type of the vector, maybe we could say we could do bounds checking in here too, right? So that's the length of the vector. Okay, so we're going to say I wish there were sort of a pattern matchy thing that we could do here, but let's do case on the expression. If it's an integer, I. If it's anything else, then we're going to return error, type error. Its vector index is not integer, e. Okay, so if it's an integer, then it needs to be strictly less than the length. So we could do a case here if I less than length, then we'll return okay I. If it's still an integer and it's not less than the length, then we will say error vector index out of bounds, and that takes actual is I and the size is length. Okay, that's pretty straightforward. So now we can go up here and we can say we've type checked v, and now we can say result try, and then we call it check vector index, and we have I think that we need to do another one, which is vector types, which will take this VT I say is vector type. I'm mostly kind of thinking of the ergonomics here. And this is going to be list of type, or a type error. Just thinking about like things that we can reuse in some of the other functions or in some of the other operators. Okay, so is vector type. What we want to do here is it's going to take a t, which is a type, with case t of vector t, and we're going to return OK ts. Otherwise, we're going to return error, type error, and this takes actual was t, expected was vector t. Excuse me. There's a lot more contextual things that we could do with the context of, you know, do we have an index on this? So we expect it to be of at least of this length, but you know, we don't really have a like any vector type, which we could put in there, but okay. And the problem is this needs an expression. So okay. So now what we'll do is this let's reuse this. Okay, so So this will simplify the vector length thing, because we now have we don't care, this doesn't change the type, right? So we don't care about extracting the list of contained types in this one, but we can do, is this type T a vector type? Okay, that's nicer. So I kind of want to just delete all this and redo it. Let's redo it. Okay, so we want to type check. We want to type check V. So we're going to type check that expression within the environment. And then we're going to use check vector index. So actually we want vector type. So we're going to do use items there and say result try is vector type, and it's that requires an expression which is v1 and t1. Okay, so that's a list of types, and then what we'll do is we'll say use I is result map index is the expression, and the length is length items. Is that right? Oh, well, it helps if I check vector index. I was like, what's going on here? Okay. Okay, and then it's just like unused variable. Okay, so now what we can do is say this vector ref is the type that it should return should be the type of the ith element of the items. So let's rename that to like item types. Okay, so what we're going to return here is v1, and then we're going to go lists at nth. All right. Let's look at the standard lib because I can't remember what that is. I thought it was at or something like that. Is that literally not part of this? That's interesting. So, yeah, I think we kind of need something that will be that will fail. I mean, we're already checking that the index is within. Um, so if the index is 0 index and we do drop, um, so we can let item type is item types list.drop I, right? So we'll drop. So if it's a 0, we'll still have the first one. And then first is like head. So in order to be a little bit paranoid, let's do this. We're going to switch this to try, right? And we'll do map on this last one. The problem might be that this will not return a type error. The other thing that we could do is because this is like we've already done all the checks, if we do case list.drop from item types I, and we get item type, if we get anything else, we should panic as we'll say invalid type indexing. Like there's no reason. Okay, so this actually, what we need to return here is vector ref. We need to return primop. This is supposed to return a primop, yeah, of v1 index, or we'll just say, yeah, v1 index. Okay. We'll say vector ref, just for clarity there. And I think that, like in this situation, if we've checked that this is a valid vector and that the vector index is in bounds and we somehow don't get the right number of types, we have a serious bug. So I think that this is a reasonable way to do this. Okay, so now we can use this sort of as a template for this. So we know that okay. So here we're going to do, there's one more check we need. So we're going to get the The other thing that we could do here, I guess I should have the easier way, right? Was going to be to say let assert. I don't know why I forgot about that. And that's going to be list first of list drop item types. And then we can get rid of this bit. So what we'll do there is we'll do something similar down here rather than this. Okay, so now we have the item type, and then we can say the result.map check type equal so I'm sorry, we need to check the type of value as well. Okay, so we'll use pt1. My variable naming is awful. Sorry, folks. Type check expression value in v. Okay, so we need to check that this takes right. So we want to make sure that the item type is the expected, right? The actual value type is VT1. Yeah, could be worse. At least the scope of this is pretty small. Okay, and then the expression is we have to reconstruct this vector set of v1 index val1, right? So that's the expression. Okay, and then if all of that works, we're going to return vector set of v1 index vt or val1, and the type of this is always going to be void t. Okay. All right, so we have our type checking for our new operations. That took a bit longer than I wanted, but wasn't too bad. So now we need to do some interpreting. Okay, so hopefully, now we can do add missing patterns. Okay, so if we're going to create a vector of fields, what we're going to do is we're going to construct a vector value, right? So this is going to be vector value. We need to first get the values that are from the result of evaluating the fields, interpreting the fields. So let's do did we do something interesting in begin in interpretation? Oh, this is interpret op. So here's begin. We do list fold. so we'll just do list fold. Okay, so we're going to do field values. Actually, we don't want to do fold. We want to do map, right? We're going to map over fields. Well, I take that back. What we want, because these are, there's nothing that says these have to be non-side affecting. We need to fold. I think there's a map fold. Yeah, we want map fold. Yeah. We want to fold over the E and V. The field is F. Okay, so we're going to do and map fold requires us to return the accumulator first. So we will return E1 and V. So this is really more like pair.flip. I need to import Gleam pair. Am I imagining it? Is it pair? Yeah, there it is. Or it's not flip, it's swap. Okay, that's fine. Pair swap. Okay, so this is going to be vector value, and it's going to contain field values. And except this map fold is going to return a new environment, right? And then we'll do env. Okay, so let's do vector length. So we just need the vector value, and the environment is going to be interpret expression v, and then we will return this is an int value of we need to do a let assert here. This is going to be a vector value. And we're going to say list.length of VFs, right? And env. Okay. And then we've got some business here with getting fields out and setting fields. So this is going to get tricky. In that vector set, we don't have mutable stuff in It actually doesn't matter for ref and length because they, it's fine to pass a vector to length and just get the length of it, which is kind of pointless. But the if we look at for vector ref, again, it's also fine. But for vector set, we're going to have to do some extra stuff there. So like if this expression is a variable, then we need to like go into the vector and update it. And if it's the only other thing it could be is a vector value. So like we could interpret the expression. And then let's see what happens up here in let. We'll insert a new. The problem here is aliasing. Like we're gonna have to have a way to express aliases for vectors. Like we don't, this plain environment, which is a dictionary of variable names to literal or concrete values. We're going to need a different concept there. Because it's possible to, now that we have things on the heap, it's possible for something to be an alias of another thing, and then if you update that thing, you want the semantics are you want the aliased thing to be updated. So maybe we need something else here. And what I mean by that is maybe when you construct a vector, okay, so when we construct a vector, I think what we want to do is, instead of returning the direct vector value, what we want to do is make a heap reference, right? So vectors are always created on the heap. So what we do is we start we have another thing. So like the env becomes more than just a dictionary. So like we need a heap type, right? Our heap is going to be honestly, right now it could be a list. We don't really want it to be a list though. Let's do a dictionary of int to, and remember only vectors are on the heap, so we can say it's a list of I value. So that's the contents of the vector. And then the vector value, we're gonna not do that. What we're gonna say is our environment, let's make, this is going to be env, and this is, the variables are going to be this, and then the heap is going to be a heap, right? And the it's just going to say it's unused. The I value is not going to be a vector value, but there's going to be a heap ref, which is going to have an index onto the heap. Okay, now we're gonna have to change all sorts of things. So let's make a quick function, new env, which is going to return env, and we'll just do env dict new. Okay. Okay, and then we'll make some simple things here where we say bind variable, which is going to be v is a string, value is an I value, and this is going to take env, and it's going to return an env. So this is going to be vars dict insert e.vars v value. Okay, except I've got my dots the wrong way. Okay, and then it's going to be we're going to say allocate vec, and this is going to take the environment. And this is going to take the like the contents. We'll call it fields. It's a list of I value, and this is going to return an integer, which is the heap ref. Or maybe we'll just say I value, and it'll just always return heap ref and env. Okay, so so here we're going to return, we'll just say let next as dict dot size of e dot heap. My cat is not happy. Yeah, e dot heap. Okay. And then we're going to say it'll return yeah. So we're kind of pretending like this is a stack, but we need to index into it arbitrarily, so I didn't want to use a list to represent it. So we're just kind of making arbitrary integers as the slots on the heap. So we're going to say this is going to return a heap ref. If it's size 0, we'll insert 0. So heap ref next is the I value that we get for allocating that vec. And then we're going to say we're going to return env. And heap is going to be, we're going to insert into that dictionary of e.heap, next, and fields. Okay. So now we're potentially more accurately representing this, but down here what we need to do is we need to say, rather than this, this dictionary insert, we replace that with bindvar. Okay, so now when we go, okay, so this is bindvar for setbang. Okay, so now when we make a vector, this is literally allocate vec, right? Because we're returning a heap ref. So allocate vec takes the environment and the field values. So it's like, it's less like directly returning the thing. Now what we need to do here is say this needs to be a heap ref, right? And then we need to do let assert okay why don't we say there's, like, make a function here that's get allocate vec, let's say get heap or yeah, and this is going to return a result, list of I value or nil, and it'll just be dict.get of e heap I. Okay, so we can say oh, here, get heap okay. So obviously if we have a heap ref which doesn't exist in the heap, then that should blow up. Okay, so now we have a similar thing here for vector ref. So what we'll do is we'll do heap ref I. So interpret that expression, and then we will do, we're going to get the values off of the heap. And then we're going to do another let assert okay, which is going to be list first, list drop of vfields index. Except index is a, yeah. So we, I'm sorry, needed to fix that. Remember, we needed to make sure that we need to make sure that this is an int. This expression. And then we'll look up I. And so this could have side effects. We don't know what's going to be in this expression. We know that vector ref has to be an int. That's why we do this assert here. And then we'll go, we'll return the value and the updated env. Okay, so that's not so bad. And we can do vector set now. So we need to do this. Actually, we're going to do a lot of the same stuff. Okay, so what we're going to do now, we're not going to extract the value. We're going to replace. So let's see what we can do in list. Yeah, there's no like put this thing at this spot. So we may have to make that function. Like I would love to use tuples to represent these, but the problem is that we need to know in Gleam its tuples need to be known at compile time. But what we're doing here is we're hosting another language where we don't know its tuples when we're trying to interpret the syntax, right? So we need something like, so if we do split, so splitting at 0 would give you an empty list first and the tail. So it's always like replace the first thing here. Okay, so if we get the value off of the heap, and we have allocate vec. Let's do update heap int fields list of I value, and this is going to return an env. So we'll do env heap is dict insert dot heap I fields. Honestly, we can do update heap here. And then it's the same. We can reuse it. Okay. So we're going to have to do another let assert. And we're going to say the predecessors field rest, or we can say successors list split of VFs at I, right? And then what we want to do is we need to interpret the value now that we know that it will fit. And honestly, we're going to drop that field. We don't care about it. We just care that there's at least one. I'm going to say underscore field like that. So we need to new field, we'll call it interpret expression of value env. Okay, and then what we can do is we keep rebinding env. It's fine. Update heap. So we're going to update heap of env with the heap ref we're going to do list append. So we need to append new field successors. Okay, and then here's the fun part. This returns void. Void value and the updated environment, right? Because this is completely mutating. Wow, that was a lot. Okay, let's walk through this so we understand completely. First, we know that the index has to be a static integer. So that's that assertion. Then this vector we're trying to set a value in needs to be a heap ref. So we're going to interpret this expression and hope that it returns a heap reference. And then we're going to get the contents of that vector off the heap, and that's what this vfs is. And then we know that we want to set the thing at the index here. So we're going to split the contents of the fields such that we get the things that come before and after that index. And if the index is 0, and we get we'll get this contains nothing, and this is just the first field in that list. Okay, so we're splitting the fields on the index, and then we're going to interpret the value. So we're going to interpret that expression so that we know what we're going to put into that field. And then we have a new value for that, and if that contained any mutating bits, those will get updated. And then we're going to, now that we have that new field, we're going to update the vector that's on the heap to be this new, like replacing that field. So list append just says put this list or concatenate these two lists together, basically. And this list will be like everything that came after the field plus the new field, and then everything that came before the field. And finally, vector set returns void, and then we have the updated environment. So I think that we've got the semantics correct now. That feels really good. It was kind of a wild ride there, a bit more than I expected. But I want to walk through this stuff. And what we can do is let's go ahead and make a test, because I want to test interpretation. And actually we might want to, let's see, we've got 20 minutes left in my normal time. We might want to update the parser, the parse pass, so that we can produce this language. So let's have a look at that. We have keywords here. We might need that. Yeah, we're going to have to do this. This is fine. So let's make a keyword vector, and vector ref, and vector set, and vector length. Okay. And yeah, so let's just add those. Vector is going to be keyword vector. Vector ref is going to be keyword vector ref. Vector set and vector length. I I think that's what they did. Yeah, vector length. Okay, except it's vector set bang. Yep. Vector set bang. Vector length is keyword. Vector length. Okay, so that aligns sort of with this set bang. The other thing I think that we need to look at, maybe we don't. I was wondering if we need to look at the if we need to look at the how we interpret our two things equal. Like, I don't think that it was doing deep equal in the book. I think we were looking at, right, so here's how we interpret EQ. This is just saying, are these the same type? These are just type checks, but we have variants for that. So I think that the variants are okay. There's a little bit in here. Like I mentioned, this has type, right? There's a bit here where the type checker they're saying should wrap certain expressions. We'll get to that. Yeah, okay. So yeah, okay, so they're saying here, consider the following example in which T1 and T2 refer to the same tuple value, and T3 refers to a different tuple value with equal elements. The result of the program is reduced. So they're saying the only way that can happen is if T1 and T2 are equal because they refer to the same place on the heap, and T1 and T3 are not equal because even though they have equivalent contents, they do not refer to the same spot on the heap. Therefore, this is false. That makes this expression true, and the entire and is true, and so you return 42. Okay, so I think that our semantics there are the same, in that we are now our I values. We're gonna go. We have a heap ref, and this is essentially how we're doing aliasing. We could have called that pointer. Yeah, so I think we're getting the right thing there, and we somehow don't have any problems. Okay, so if I go down here to compare equal, yeah, it's just checking that in the type checker, it's just checking that those are the same type. Yeah. And then the interpreter for equal. We need to add another thing here. Which is heap ref. Okay. Okay. Then they're the same type, and we can say, yeah, they are equal to one another. Okay, so what we were going to get before I did that was we were going to get this would panic because we didn't account for that type. Okay. Pretty good. Okay, so what I was going to do, let's finish our parser. Let's look at adding parsers for these concrete expressions. And I think I'm going to hide that, and we're going to pull it over here to the side. So let's make, all right, kind of have the terminals down here at the bottom. Okay, so let's make vector op, and this is going to return a parser of a prim op, token nil, just like the rest of these things. Okay, so we're going to say what we want is a token of keyword vector. That's going to be the start. And then we're going to have to look at nibble again because it's been a while since I've looked at it. Nibble. All right. So we're probably going to do nibble many. Yeah, and that'll return a list. Yeah, we're already kind of, for these things, we don't require the separator. So because the separator is just white space, so I think we can do many. The question is, does it make sense to have a vector of 0 elements? It's kind of silly, but I don't think that there's anything limiting our language from having that. I don't know why you would do it, but you just like throwing things on the heap for no reason. Okay, so let's do many. Use fields, we'll call it that. Many expression. And then we'll return. And here we need to go up here and say this is ltup, right? And we need to say this is lang.vector. Yeah. Fields. That wasn't too bad. So now let's. Sorry, that is not relevant. Minimize that. We can just close that. Give me a second. Okay, we'll just pull it off the screen there. Yeah, so let's do vector length. This one, we need the vector length keyword. Okay. And then there's only one expression in it. And then we will do a return arg1. And this will be, we'll do something similar for vector ref. Use arg2, do expression. And this is be vector ref. arg1 and arg2. And finally, vector set. Now, there's an interesting thing again here where we could choose at the parsing stage to disallow construction of invalid ops there. We have the checks over here in our language, though, both in the type checking. So, you know, in these bits where we're type checking the vector index, right? And so forth. So we, you know, that's kind of a semantic analysis thing, but technically speaking, it's invalid to put anything but a statically defined integer into that index field. So we just sort of allow it right now. Okay, so we have vector, vector length, vector ref, vector set. And now we'll just add them onto the end here. Vector op, vector length op, ref op, vector set op. And that was, you know, it's nice that we did this sort of structure previously, because that made it really easy to extend. Cool. Okay. Now that we've got that, vector, vector length, vector ref, vector set. Okay. So let's go back to what we were going to do a moment ago. Let's make a test. Say ltup test. And we'll kind of do some of the same things that ltup does. There is a problem here in that we are our parse thing. The thing is, we didn't do it in these other ones. We were using straight up ASTs. So I think that like this test is going to fail now that we've changed parse, because parse is producing ltup rather than lwhile, and we can already see that here. We're going to do that. That's fun. uh, I'm going to say vector at yeah, I don't know. We'll just say vector. We're going to have to deal with that again later, but yeah, and none of this will compile. So let's just revert all of that. Yeah. We're running up close to the end of time. I think that I want to go ahead and write this test, and probably what we could do is we don't absolutely have to preserve all of the previous versions of our language in this. Like, we are evolving this. And I wish that what I had done when we added this file was made it a language specific pass. The other possibility is that we can do something in here like or in the new updated language that downgrades it into the previous one. I don't particularly like that. Some of the things that, like, this is one of those things that if we were doing this in Racket, as the book suggests, we wouldn't have this problem, because it's just open-ended lists for the AST. Not strictly, but like it's essentially more open-ended than this. We have to be strict, and know the types of our AST at compile time. Okay. Well, I think, what we're going to find is that this stuff just, like, fails. Fails to compile. So we're going to have to turn it off. And what we can do here is comment this out, and we can say error not implemented. And we can do the same down here, and then we can just restore it when we're ready. And then like, I don't care about the warnings. We can deal with the warnings. Now here, what we should do is just comment out this test, and that will, these other passes will probably break. Like, we can see explicate control probably has some parsing in it. let's see where that error is. Yeah, this. We're going to have to comment out that test so we can run the tests. Well, let's comment this out and then see the areas where it broke. Yeah, so this test needs to be commented out. What's the other one? This one. Yes, the ones that were associated with chapter 5. Okay, now parse test. We need to say this is L tup. At least it compiles. I don't know if it passes. Okay, so now we're down to remove complex operands. Yep, it's got some ones. So let's go down here and wish there were a better way to do that, but okay, it's just the RCO loops. Okay, and select instructions. And yeah, this is gonna have to be L-tup. Like, lots of things are gonna break. Honestly, I think we're just going to comment out the entire file. We're going to have to do this with everything until we get the entire stack going. Okay, so now now at least I'm not getting any compilation errors. Tons of warnings, probably about unused. Okay, so let's do like what we did here. And the whole goal of this was going to be, I want to test interpretation for those examples that are in the book, where we know, and type checking, right? So we'll start with that. Okay, and we're going to make our own, again, we're going to make a parsed helper here, which is input string, and it's going to return ltup.program. So we'll say input parse.tokens should be okay. Parse.parse. Isn't that what we called it? Yep. Should be okay. Okay, that's the basic thing that we were doing before. And this is L, not L-tup. Okay, so let's copy this program. Okay, and then we should say pl.interpret. Should.equal int value 42. And I think like if we get this, and actually we don't need to set that as a separate thing. We can just do pass it to parse, pass it to interpret, pass it to should equal. That should be, yeah. We should get an int value 42. Okay, so that passed. Let's do, this is a good one as well, because that tests our so we're testing aliasing, right? This should all, they love 42 in this book. Okay, so we should test that. So we're still doing good. Our interpreter is correct. And this last one, let's see. Following program returns 42 even though the variable w goes out of scope. Okay, so this is about scoping. Yep. Scope interpret test. We call it like lifetime. Yeah, I don't know what the indentation is. Oh, okay, it should be out a little bit. Yeah, that's kind of weird. Actually, this one is further in. It's like aligned with that or something. No, aligned with that. Okay. Regardless, another one that returns 42. Okay, so at least those are correct so far. I think this is a good place to stop. Next time we should add some tests for our type checker, and then we can get on with doing the rest of this. So like starting to go through the phases, adding the new phase that does exposes allocation. I think that's what it's called. And we'll see you next week. Thank you so much. This has been fun. Good to see you.